Good morning everyone. Last video we have discussed about the valence shell electron pair repulsion theory. We have discussed about the octet rule, and now we are going to discuss about the valence bond theory. Before that, we will discuss that why we are not sticking with the valence shell electron pair repulsion theory. There was some problem with the valence shell electron pair theory. That means it was not capable to explain the energy of the molecules properly. That was not perfectly fit for those of the multicentric species and some other problems like the bond energy. So the new method came, the new concept came for the explanation of the molecules, and that new concept is called the valence bond theory. This is the completely new theory. The valence bond theory says that whatever the property is shown by the system, that is not the property of the simple orbitals. That means the simple orbitals are not going to take part in the chemical reaction. That is not, they are not going to take part in the bond formation. It is the hybrid orbital which will participate in the chemical reaction, and it is the hybridization which is important in this process. That means it is not the S subshell or the P subshell or the orbital of S subshell and orbital of P subshell which will take part in the reaction. It will be the hybrid orbital, that is the mix of the S and P, which will take part in the reaction. When we talk about the hybridization, you talk about the hybridization a lot at your home, the hybrid vegetables, hybrid animals and so many other things. Then what is the hybridization first? We say the hybridization is just like mixing of color. You have mixed the color and you have find that after mixing the color a new color arises. For example, if you are mixing red with white, what is the new color? It will be pink. And what is pink? The pink contains the property of red as well as the property of white. But when you will see that whether the pink is red, surely not, and neither it is white. So the new color contains the property of white as well as the red, but that is neither white nor red, and this is the condition of the hybridization. When two different species of almost identical energy combines with each other, they form a new species containing the property of both the parent systems. But they are neither the first parent system nor the second parent system. They are totally different. Only they carry the property of that one. Similar thing is happening here. The orbitals of almost identical energy, when mixed with each other, they generate the hybrid orbital. So here you can say that this is the first orbital of S subshell. Spherical shape, no node, perfect spherical system. And second one is the orbital of P subshell, a dumbbell shaped species having a node in the center and perfect dumbbell shape. So when these two will combine with each other, they will generate two hybrid orbitals. That is this one. This lobe is containing extra property of the S subshell. That means the lobe is not in the center, that is on the one side. That means the lobe is shifted. So the S property increases as well as the system is containing the P property, that is containing S property, that is containing P property. But when you will say whether it is S orbital or the P orbital, that is neither the S orbital nor the P orbital. This is the sp hybrid orbital. It means one of the S is hybridized with the one of the P. As one S is hybrid with one P, it is the sp hybrid. If one S hybridized with 2P, it will be sp2, 3P, sp3 and so on. So this is the hybridization, and these of the hybrid orbitals are responsible to represent the property, to represent the structure of the system. How will you find that what is the hybridization in a compound? Here I have said कि एक S एक P से होता है तो sp, एक S दो P के साथ होता है तो sp2 वगैरह वगैरह, लेकिन कंपाउंड देख के आप कैसे पहचानेंगे? कि sp है, sp2 है, sp3 है. For that purpose we will calculate the number of hybrid orbitals. How many hybrid orbitals are there? And how will you calculate the number of hybrid orbitals? We will calculate with the help of the lone pair and bond pair. That means the number of lone pair plus bond pair equal to hybrid orbitals. So we are seeing how to find the number of hybrid orbitals. Here I have already written the number of hybrid orbitals equal to lone pair plus bond pair. What is the lone pair and bond pair? The bonded valence shell electrons are called the bond pair and unbonded valence shell electrons are called the lone pair, simply. But if the bond is a single bond, double bond or triple bond, the lone pair will be considered just one. सिंगल बॉन्ड होगा तो भी एक लोन पेयर कंसीडर करेंगे, डबल बॉन्ड होगा तो भी एक ही लोन पेयर कंसीडर करेंगे और ट्रिपल बॉन्ड में भी एक ही लोन पेयर कंसीडर करेंगे. सो द लोन पेयर मीन्स द अनबॉन्डेड वैलेंस शेल इलेक्ट्रॉन एंड द बॉन्ड पेयर मीन्स द बॉन्डेड वैलेंस शेल इलेक्ट्रॉन. हियर आई एम टेकिंग एग्जांपल ऑफ द अमोनिया NH3. Nitrogen having 5 electron in their valence shell, 1, 2, 3, 4 and 5. And 3 hydrogens are making the bond. That means the 3 bonds are there. So what is the number of bond pair? 3. 3 bonds are carrying the 3 bond pair and 1 pair of electron is here which is unbonded, which is not bonded with any of the species. So this one is called a lone pair. So what is the number of the total hybrid orbital? 3 plus 1, that is the lone pair plus bond pair, and that is 4. So here is the number of hybrid orbitals. This is the way how will you find the number of hybrid orbitals. Now we are relating the number of hybrid orbitals with the hybridization and shape. What will be the hybridization and what will be the shape of the compound with the different number of the hybrid orbitals. So we are getting that what will be the hybridization and shape. So we are going to relate it here. When we see the hybridization, the number of hybrid orbital may not be 1. अकेले कैसे हाइब्रिड करेगा, किसके साथ हाइब्रिड करेगा? So we are starting with the 2 hybrid orbitals. If 2 hybrid orbitals are there, then what will be the hybridization? There will be one S and one P. If we are seeing in this sequence, this will be the sequence for the hybridization. So one S is hybridizing with the one P. That means the hybridization will be sp, and with the sp hybridization the system will behave like a ab2 type of molecule having bond pair plus lone pair equal to 2. So the shape will be just linear for such system. So the sp hybridization suggests the linear shape. But if the number of hybrid orbital is 3, then what will be the hybridization? 1s will hybrid with 2p. Then what will be the hybridization? The hybridization will be sp2. sp2. And what will be the shape here? And this time the shape will be similar to that of the ab3 type of compound, that is the trigonal planar. When the number of hybrid orbital is 4, the hybridization will be 1s and 3p, that is the sp3, and the shape of the molecule will be tetrahedral. In case when the number of hybrid orbital is 5, the hybridization will be 1s and 3p, because 4p is not available. Only 3 orbitals in the p subshell is available. So 1s and 3p along with one of the d orbital from the d subshell. So it will be sp3d, and the shape will be trigonal bipyramidal. In the case when there is not all the all the bond pairs are available, one lone pair and 3 bond pair is available. In those of the cases, this tetrahedral shape can also survive in the form of the trigonal bipyramidal. Now we are seeing the 6 hybrid orbitals. When the number of hybrid orbital is 6, now what will be the hybridization? sp3d2. You know how we find the hybridization. And in this case, sp3d2, the shape will be octahedral. And the last one, when the number of hybrid orbital is 7, it will be sp3d3, and the shape will be pentagonal bipyramidal distorted. Pentagonal bipyramidal distorted. So these are the different number of hybrid orbitals, hybridization, and the shape related with that hybridization. It's over for today. In the next class, we will discuss the next topic. Till then, have a nice day. Thank you. Bye.